All right, let's jump into chapter 10, part 2, starting with the 5 mechanisms of drug resistance. What I need you to know is the 5 types, those mechanisms of drug resistance, as well as how did the microbe get that drug resistance. So the first one is that new enzymes are made from that inactive drug. So this is going to occur from acquisition. Then we have permeability or uptake of the drug into the bacterium being decreased. So this is how much of the drug is able to get into the cell itself. This occurs from mutation. And then next is that the drug is immediately eliminated from the cell. This occurs from acquisition. Next is that the binding sites for drugs are decreased in number and or affinity of the binding sites are lowered. Remember that the binding sites are kind of like those locks where a key has to fit the lock. So what we're saying here is that lock essentially is changing, or we're changing the number of locks essentially. And this can occur by either mutation or acquisition. And then the last one is that an affected metabolic pathway is shut down or an alternative pathway is used. And the example is something that we talked about at the end of chapter 10, part 1, and those are persisters. And this is going to happen through mutation. So when it comes to natural selection of drug resistance within microbes, we've seen now how that drug resistance can occur at a cellular or molecular level, but in terms of human health, it's typically going to happen at a much higher level as far as like populations go. So let's look at whole populations of species that become antibiotic resistant and how that's going to happen. I've got a nice little imagery for you here in just a second. So what we've got going on in that first image is we have some mutants, those orange kind of kidney bean shaped cells that are living amongst our other species of cells, so these bacteria. And the orange ones are going to be these mutants that are just kind of hanging out within the rest of the population. They are antibiotic resistant, those orange ones. Now, if we were to introduce antibiotics into this population of bacteria, what we would see is all of those blue cells, whatever species they might be. Maybe there's different species because we see different sizes of those cells there. Maybe that's indicating different species. All of those bacteria are going to die. What is left is the mutants. So that is going to change the space and resources available to the mutants. So if we're looking at this potentially inside of our body and we introduce antibiotics into our body, right? We are going to kill off, if we use a broad spectrum antimicrobial, we're going to kill off all of our good bacteria, the blue bacteria there. And what's left is those antibiotic resistant, potentially bad bacteria. And now they have nothing but resources and space because our home team, our good bacteria, are gone. So in that third panel, what we see is the antibiotic resistant bacteria growing and taking over because, again, they have all of this space, all of these resources, food, all kinds of stuff. And there's no other species that they need to compete with, essentially. Now, what we start seeing in that fourth panel is that some of the bacteria are able to, through acquisition, share their antibiotic resistance with other bacteria, which is going to cause more problems, potentially like MRSA, that we see in hospitals, that antibiotic resistant version of bacteria that we find living on our own skin, but it shouldn't be antibiotic resistant. So that is kind of how antibiotic resistance can happen. So I would know this process just kind of in general, how it can happen and why it can be so scary. So let's talk about how big this threat actually is and who's dealing with it. I keep using this phrase, the post-antibiotic era. So again, what I'm referring to here is this time period in which we aren't able to effectively use antibiotics to treat bacterial infections. So this became kind of a bigger issue to discuss in 2013. It was brought up by the CDC and issued as a threat report. So the problem is that there still hasn't really been an answer in the last couple of years as far as what to do, how to do it, what should we be doing. So much so to the point that 3 years after the CDC issued that this post antibiotic era that we are entering into, that we can't treat infections with antibiotics, could be really catastrophic. In 2016, the UN met, and to kind of give you an idea that since the UN, the United Nations, formed, and mind you, this is a global combining of countries. Since they formed sometime around World War II, they've only met 5 times. So this is one of those times that they met to talk about this post-antibiotic era. Again, the question is, what can we do to start fighting back against bacteria and microbes that we can't fight with antibiotics? So, unfortunately, the prediction is that by 2050, antibiotics will be essentially useless. And that date, that year, is fast approaching, and we don't have an answer, really. Now, I wouldn't be so mad at the microbes if they weren't also living organisms just trying to survive, essentially us, but we're also trying to survive them. So the biggest issue is we just don't want to go backwards to where we were, and that was barely surviving, essentially like paper cuts, because we can't fight those infections. So other organizations, like the World Health Organization, began a campaign to combat against antibiotic resistance in 2015 due to the real push and urgency of the situation of realizing, holy crap, we really can't go backwards. And 2050, that prediction, that's really starting to look like that's going to happen. So we really need to start doing something. So what did we start doing? Well, we started looking at new and effective antibiotics because that's the natural next step, trying to find something to help fight those microbes. The caveat to that is capitalism. There is no market, no profit in making new antibiotics. You would think that saving the world and saving people's lives would be initiative enough, but shockingly, it's money. And there's not really any economic value in making something that you use once, saves your life, and then you don't use again, right? So, the other issue is that the research is very slow. And then that other side, of course, capitalism is that it's very expensive and you're making no profit. So those are the two big issues that are kind of the hang-ups of why we have had little to no success in finding new and effective antibiotics. Now, some policymakers are trying to make these incentives for drug companies to focus on making short-term antibiotics, but again, because there's not a whole lot of profit and the research is really slow, we are not finding a whole lot of movement when it comes to this particular method. And unfortunately, in the meantime, microbes are still evolving to have antimicrobial resistance. So let's talk about those levels of resistance. So this is coming straight from the CDC. What I want you to know are the 3 levels and how many organisms fall within those levels of essentially resistance. So starting at the bottom here, we have concerning threats. There are 2. Serious threats, there are 11. And in urgent threats, there are 5. And the urgent threats are the one that I actually want you to know all 5 of them. That is C. diff, CRE, superclap, which is gonorrhea, Candida auris, that is a type of yeast infection, and then CRA. So these are the 5 urgent threats that I want you to know by name. I don't need you to know the 11 serious threats. I don't need you to know the 2 concerning threats. I want you to specifically know the 5 urgent threats. Okay? Know the 3 levels of resistance and how many in each one. The urgent threats is the only one that's a little bit different. Now, in the US alone, 2.8 million people a year are infected with resistant bacteria. Of that 2.8 million, 35,000 people die from that resistant bacteria alone. So, what works against this crazy antimicrobial resistant bacteria? And the answer is this polymyxin. We've talked about it a little bit before. But what I need you to know about polymyxin is it's the last resort drug. So it's a very important antimicrobial that we use quite literally as a last resort. However, and I'm so sorry, we are going to talk a little bit about doom and gloom here. We have already found out of China a gene in certain microbes called the MCR1 gene that allows bacteria to be resistant to polymyxin. Again, that is the last resort drug. So that's terrifying. However, we noticed this in 2015 and we haven't seen a whole lot of movement of this gene since. It hasn't become widespread yet. Keep in mind, we're saying yet. We fully expect that gene to jump. Now, we need to do something in the meantime to try to find ways to look at antimicrobials, new approaches to antimicrobials that can help in the meantime before that gene starts jumping and that polymyxin becomes not the last resort anymore. It becomes useless, right? So let's talk about some of those new approaches that we're looking at, some areas of study, some silver lining, if you will. So the first way that we are approaching new ways to antimicrobial therapy is that RNA interference. We talked about RNAi with fungus as far as that ability to affect those structures on the outside. But that's something that the microbe itself can do. So is it something that we can do from the outside of the cell as opposed to the cell doing it from the inside? So it's those on-off switches that regulate gene expression. So that would be kind of cool. We also talked about this a bit in chapter 7 and 8. If you wanted to refresh kind of the thought process there. So yeah, we have a couple human trials for hepatitis C, as far as being able to affect microbes from the outside and affecting their gene expression. Kind of cool. The next is defense peptides. Now, real quick, little background about defense peptides is that these are very short proteins that naturally occur in our immune system. And what they do is they puncture holes into bacterial cell walls. Um, Now, what we want to do with them is essentially make them stronger, like little drills, and give them a direction. So push them to specifically attack, kind of create them into little soldiers. What we've seen is some success, although we are still kind of in that, again, kind of trial stages here. So those are the first two approaches to new antimicrobial therapy. Again, this is all kind of silver lining, but in the early stages of what we can be doing, still testing. Another approach or method to antimicrobial therapy is one of the coolest things you've probably never heard of. And if you have, great, fantastic, I love that for you, is CRISPR. This is a DNA editing tool found naturally in bacteria, and we've stolen it, which is kind of cool. So I kind of think of this as Photoshop for DNA. What you can do using CRISPR, which is an acronym that you don't have to know what it means, I don't care about that, just know what it does, is that you can delete certain genes in the DNA of pretty much anything. It can be bacteria, it can be viruses, it can be protozoans, it can be mammals, it can be anything, guys. It's pretty crazy, but you can modify genes in anything that has DNA and affect how that gene is expressed or not expressed. So what we could do with this information, this tool, is to take bacteria, remove the gene that causes my antimicrobial resistance, and just get rid of it and make bacteria susceptible to antimicrobials, which would be fantastic on paper. However, there are two issues when it comes to CRISPR, and I want you to know those two problems. One, there is a legal battle of who gets the credit and profit, because it all comes back to capitalism, y'all. The second issue is ethics. Editing the genes of bacteria doesn't seem like it'd be an ethical issue, because I don't think it would be. The problem comes from, where do we stop? We can and we have used CRISPR to change the DNA of other organisms. For example, we have changed the DNA of mosquitoes that carry malaria to not carry malaria, which is crazy cool. However, if we can do that to mosquitoes, that doesn't stop there. You can essentially use this on humans and modify the DNA of humans. And what I tongue-in-cheek kind of call build a baby, CRISPR can be used to build humans with certain parameters of what you want. You want your baby to have green eyes and red hair and specifically have freckles and look absolutely darling and also have this particular intelligence and this athletic aptitude and etc. etc. Essentially, you could create a laundry list of what you want your baby to be. And that has a lot of ethical ramifications. So there are a couple issues when it comes to CRISPR, and that is why it won't be used, most likely, for many, many years to actually benefit society. Next is that drugs from non-cultivable, hard word, cultivable bacteria can be discovered. So 99% of bacteria, and that seems like a high number because it is, of bacteria can't be grown in a lab. And if it can't be grown in a lab, we can't really study it under the parameters that we need to find new antibiotics. So if we can start being able to grow bacteria that we haven't been able to grow in a lab before, then we can start studying the bacteria and discovering new antimicrobial substances, which would be really, really cool. For example, a group of students out of Massachusetts created a special chamber to grow bacteria, and by accident discovered something called Texobactin, which is a new antibiotic that so far a lot of bacteria have become very slow to become resistant to, which is really cool. And again, they weren't looking for antibiotics. It was a complete accident that they happened across this Texobactin. And it was just because they were trying to grow this particular bacteria in their special little chamber. So, if we can start cultivating this bacteria that we haven't been able to cultivate before, who knows what we would find? The next one is essentially teaming up with something that we've already talked about quite a few times, and that is bacteriophages. Bacteriophages are viruses that only target bacteria. So, prior to penicillin, so in the 1930s and 40s-ish, what was formerly the Soviet Union was looking into weaponizing bacteriophages to attack bacterial infections, which is crazy cool. However, when penicillin was discovered, almost all of that research was scrapped or put on hold until more recently, because penicillin and other antibiotics were the way to go. So why look into this method if we found something that worked? So we've lost a lot of time and ground and research using bacteriophages because we thought we found the method. We thought we found antibiotics. So now we are starting to look back at those bacteriophages and saying, hey, can we start using this virus to attack bacteria in these infections? And the answer is, yeah, we've had some human trials with ear infections that have worked pretty well. And what's cool about bacteriophages is they don't affect our cells. However, there is a little bit of concern that bacteriophages could attack our good bacteria, our home team. And again, there are just some trials for this as far as using bacteriophages as our kind of like little soldiers, if you will. Not dissimilar to our defense peptides, those little proteins that we were talking about just before. We are going to start talking about our home team now. And our home team is one of the best ways that we are able to fight off infections, because our home team is going to work for us because it doesn't want other microbes growing in or around or on us. So, how do we help our home team essentially stay strong so that we don't get infected? Well, there's probiotics and prebiotics. Make sure you know the difference. Probiotics are going to rebuild the home team if something becomes kind of unstable in there. So this is essentially the process of ingesting good bacteria. I like to think of the absolutely illustrious Jamie Lee Curtis and her Activia commercials. So those are a bunch of like probiotic yogurts that were really encouraged back in the day. It wasn't that long ago, is what it feels like. But there was a big push for probiotics to consume good bacteria for good gut health. That is very important. It can be very useful in fighting infections as well as managing food allergies as well. So super important. Another thing that we can do is prebiotics. Now, this isn't consuming good bacteria, it's feeding the bacteria that is already inside of you. So, it's feeding your home team the good things that it wants. So, foods like garlic, and remember, we always measure garlic with our heart and our soul because garlic is very good for your home team. They love it, it's very nourishing for them. Tomatoes are super good for our home team, leeks, and jicama, which is essentially like a dirt tomato. But hey, I'm not here to judge. These are ideal foods that will nourish the home team and keep them strong so they can fight the bad microbes that we don't want within our system because they are one of our first lines of defense um, against a microbe, a pathogen, if it gets into our system. We'll talk about that more coming up. So another interaction that we need to talk about is drugs and us. So drugs specifically being those antimicrobials, right? So how do we interact with the drugs that we're prescribing? So more often than not, when something goes wrong, as far as when we take those antimicrobial drugs, it's our body having some type of reaction to that drug itself. So there are three major side effects, and they are going to fall into one of these three categories: direct damage to tissues through toxicity, allergic reactions, and disruption in the balance of normal microbiota. So let's talk about each one individually. So when it comes to toxicity to our organs, it's going to come down to the location of where that toxicity is occurring. So if that toxicity is happening in the liver, we're calling it hepatotoxic. We're saying that that toxicity is happening in the liver. Again, we're talking about the location versus nephrotoxic. That means it's happening in the kidneys. And in fact, those are the only two that I really care that you understand and know, because those two organs, the liver and kidneys, technically three organs because we have two kidneys typically, within those organs, those are going to be the organs that serve the purpose of filtering out toxins. So those two organ systems are going to be the ones that get damaged more frequently when it comes to taking these antimicrobial drugs. However, I do not care if you guys know those terms: hepatotoxic, nephrotoxic. I'm sure you can understand that what we're saying is it's just saying the location of where that toxicity is occurring and causing damage. Next up is allergic reactions. So if our body responds to the drugs as if the drugs are a foreign material, we are essentially responding as if the drug is an antigen. So our body is recognizing the medication as, and I want you to write it out like this, non-self. And that means that our body is going to have an immune response and attack the drug. That is what causes that allergic reaction. So a lot of people can be allergic to penicillin as well as sulfonamides. That is something to keep an eye out for, as well as what we're going to be talking about next. When it comes to allergic reactions, the first encounter with a drug that we are allergic to typically will have no reaction. This is very important because if we are introduced to that drug again later, that second encounter is going to produce a reaction that could be maybe hives or respiratory inflammation, possibly anaphylaxis, which would be a really extreme reaction, but it could still happen. The reason that that first encounter does not result in a reaction is because our body is forming a memory to be recognized later that if that guy shows up again, we're going to have a problem. We're going to have a fight, right? So what we call this is being sensitized. That is where a memory to be recognized later in that second encounter is formed. So very important. Now, just because we have that second encounter happening, I want you to keep in mind that every subsequent encounter after that second encounter will get worse with that reaction. So those memories will come back up. Your immune system will get worse with every encounter to that drug. So we just get stronger and stronger to that reaction. That allergic response will become worse and worse. Now, that third response that we can have if our body responds to an antimicrobial is the eradication of our normal biota. So that normal microbial colonies that should be living inside of us. What this can lead to is a superinfection. So if our home team, our bacteria that lives inside and on us is completely wiped out, this is going to leave a lot of space and a lot of resources that can be utilized by pathogens, something like C. diff, which C. diff, fun fact, is an antibiotic resistant, so it can survive antibiotics. Our normal biota cannot. So if we use something like tetracycline, our normal biota is going to be wiped out. The thing that could be left is C. diff. And with all that space, all of those resources like food and whatnot, that C. diff is going to grow like crazy and lead to that super infection because there's nothing to stop it. Our home team is gone and those pathogens have nothing to compete with. So that C. diff survives and now has all of that space and resources available, goes crazy. So how did we get here? There's three primary reasons of how we got to this post-antibiotic era, and I do want you to know them kind of in a general sense. The first is that most people don't really understand the difference between a viral infection versus a bacterial infection. It's just this kind of misunderstanding that taking an antibiotic doesn't cure everything. If you have the sniffles and you're not feeling very good and you have something like the common cold, taking an antibiotic isn't going to do anything because what you have is a virus. And antibiotics treat bacteria, not viruses. So taking medication like an antibiotic when you don't need to is going to lead to these mutations over time that have gotten us essentially where we are in a very short period of time, creating those again mutations of or acquisition through acquisition. Either way, we've gotten a lot of microbes to this point by overusing antibiotics as a cure-all for anything because we haven't felt good. Um, Kind of going hand in hand with that, we have doctors who have prescribed antibiotics either lazily or they're old school doctors and they use the shotgun method of using things like tetracycline as a broad spectrum antimicrobial for minor infections instead of doing more research. And again, either it's because they're being lazy or they're more old school and that was how they were trained. It doesn't really matter. How they do it is they try to prescribe because they don't want to do the work. They don't want to put in the effort to figure out what it is they're treating, and it leads to this broad spectrum antimicrobial being given out, as well as doctors, as well as all kinds of other institutions, resorts even, will hand out antimicrobials or antibiotics just over the counter. It's too accessible to get broad spectrum antibiotics for minor infections or no infections at all. Leads to the same issue. And then our last problem is leading back to capitalism. So if antibiotics or antimicrobials are not sold here in the US, then they are going to be sold in other countries and then easily sold over the counter with no prescriptions needed. And again, these large pharma companies are going to sell this product overseas, and then it's not going to be regulated who receives these drugs. So again, we're kind of still looking at all the same issue, that antibiotics are just too widely accessible and used entirely too much. It's just the how we get to that point. So yeah, those are the three ways that how we got here to this post antibiotic era. Those are the three ways. Now, that is the end of chapter 10. Make sure you are studying. There's a lot of information here. We will jump into chapter 11 soon, and that will be the end of unit 3. So happy studying. Let me know if you have any questions at all. I am here for you guys.